Hello, my name is John Hord, and I'm a chemical engineering student here at Ohio State, and I'll be graduating in the spring of 2021. This video is part of the Active Learning Initiative as sponsored by the William G. Lowry Department of Chemical and Biomolecular Engineering and led by Quent Hart. The Active Learning Initiative aims to aid in the transition to virtual classwork specific to the chemical engineering major as necessitated by the COVID-19 pandemic. This video specifically is part of a pilot series created for CBE 2200, where each video covers a topic cogent to that course, and this video covers an introduction to psychrometric charts. I want to take you through where we're going to go, and we'll start with what exactly a psychrometric chart is, and we'll cover an intro to the chart axes and the variables that you can find within the charts. Then we'll do an example problem and get some experience using the charts, and we'll cover how the charts are useful in CBE 2200, the CBE curriculum as a whole, and even in your career. And finally, we'll wrap up with some concluding thoughts. Now, what exactly is a psychrometric chart? I've included a picture of one from the Felder and Rousseau textbook, 4th edition, on the right here, and it looks kind of messy. It's a dense collection of physical parameters for a vapor-liquid system, and this one specifically I want to point out is for water and air at 0 degrees Celsius and 1 atmosphere. You should always know the reference state. And what they really are is just those parameters plotted against one another and the relationships exhibited in graphical form. And they're very useful in balances, energy and mass balances. I want to start with the axes because those are the two things we often look at first. The x-axis is going to be your dry bulb temperature in degrees Celsius. And the dry bulb temperature is just the temperature if you were to measure it with a normal thermometer. Your y-axis is going to be moisture content in units of kilograms of moisture or water, depending on what the chart's for over kilograms of dry air or kilograms of dry gas. And it's not a dimensionless unit because it's kilograms of moisture over kilograms of dry substance. That's why it's not dimensionless. I wanted to point it out. And there are a few other parameters you might have seen on the chart, and we'll go through these in the next slide, but these are the ones you can pull directly from the chart. The enthalpy at saturation in units of kilojoules per kilograms of dry air, and then the enthalpy deviation in the same units, the relative humidity in terms of percentage, then your wet bulb and saturation temperature, those are two terms for the same thing, in units of degrees Celsius, and then your humid volume in units of meters cubed per kilogram dry air. Let's start with the saturation enthalpy and the enthalpy deviation. To find enthalpy at saturation or saturation enthalpy, they're the same thing. I wanted to include both terms. It's labeled right here, and you use the lines that go off of the chart, the negative sloping diagonal lines that extend off the chart. And then we have what are called enthalpy deviation lines. And the three that I have highlighted here are all negative, and they start kind of vertical on the right-hand side, and then they become more bowed as you get to the left end of the chart. And at the very left end here, you see that some of them are positive. Now I want to take you through how you might find your enthalpy at saturation and your enthalpy at a given point. So let's take this point. And if we wanted to find the enthalpy at saturation for that point, for that airflow, let's say, all we would do is use that diagonal line that extends off the chart and go directly up. For this point, the enthalpy at saturation would be roughly 85.4 kilojoules per kilogram dry air. Now that's at saturation. That point isn't at saturation. The saturation curve is actually the furthest most left bold line on the chart, and we'll cover it in more detail a little bit later, but this point is not on the saturation curve. Luckily, however, it falls on the negative 1.0 deviation line. So all we do to find the enthalpy at that point is we take the enthalpy at saturation, 85.4, and we add or subtract the deviation. In this case, we subtract 1.0. So the enthalpy at that point is going to be 84.4 kilojoules per kilogram dry air. Next, I want to cover relative humidity, and I'll highlight three here, 70, 60, and 50. And the way that I find them is they're always labeled with percentages, like percents. And you can see 50, 60, 70, it continues on to 80 and then 90. There isn't a 100 labeled, but the 100% relative humidity is that very last left end line, that saturation curve. That's why it's the saturation curve. At 100% relative humidity, you're fully saturated, hence the term saturation curve. Your wet bulb and saturation temperature, it is labeled, but I want to make sure that we know how to find it. And again, since it's on it's your saturation temperature, it falls on that saturation curve. But to find the saturation temperature of a given point, say the same point we were working with earlier, we do the same thing that we used to find the enthalpy. We follow those negative slope diagonal lines straight up. And for this point, the temperature are labeled along these. So we have 25 right here. For this point, it's on this diagonal. So 25, 26, 27. So this point, the wet bulb / saturation temperature is 27 degrees Celsius. And finally, I want to hit on humid volume. These are a little bit more difficult to see, so I'll highlight 3 of them. And they're kind of thin, very steep negative slope lines, and they're labeled, most of them, I should say, are labeled down by the x-axis. So we have 0.8 here, 0.85, and 0.90. The exception to that rule is right up here, 0.95. And I just want to point that out because that one's often missed. And if you're asked to find humid volume, or if you're given humid volume, I'd recommend having like a ruler, because these lines are a little bit further apart and you might have to interpolate. Say if you were given a humid volume of 0.88, that's not easily, like I can't just look at that and find it. So you might find a ruler to be useful. Now comes the fun part, how we use psychrometric charts. A lot of these parameters that are on the chart are interrelated, hence why they can be plotted against one another. So if you have 2 of them, you can find all of the others that we've just talked about. That's extremely useful in energy balances, and it has applications in mass balances as well. Now, I just said that given any 2 parameters that we just covered, you can find all the other ones. There's one exception to that, and I want to point it out because you might be like examined over it or quizzed over it, that type of deal. If you're given saturation temperature and enthalpy at saturation, since they share the same grid lines and they're found in similar manners, those will only tell you like the line that the airflow is on, and they won't allow you to find the other parameters that we've discussed. I do want to go through an example problem so you can see what kind of questions you might be asked with psychrometric charts. So let's go ahead and do that. Air within a drying process in a pet food plant has a dry bulb temperature of 27 degrees Celsius and a relative humidity of 50%. The plant engineer asks you to determine the dew point temperature within the dryers in order to determine if the winter temperatures at the plant are going to cause condensation in the dryers. What is the dew point temperature for that airflow, and should you be concerned about condensation in the dryers? So, dew point isn't explicitly labeled anywhere on this chart, but it's not labeled. However, we can find it, and I'll show you how to do that. The first step is we got to find the point on the chart, otherwise we're just staring at this thing and it's not very useful. So we know that the dry bulb temperature is 27, so I've pointed that out on the x-axis, and we know that we're on this 50% relative humidity line. So the point where those 2 lines, curves meet is right there. So to find our wet bulb temperature, we'd use those diagonal lines, but that's not what we're doing. We're finding dew point temperature, and to do that, you just go straight to the left. If you want to find dew point, you just go straight to the left, and I've highlighted that here. And the last step would be to record that, and that is 15.7 degrees Celsius as our dew point for this airflow. And that's what we would say to the plant engineer. If our temperatures are at or below 15.7 degrees Celsius, we should be concerned about condensation. If not, then we're fine. And psychrometric charts are very useful in CB 2200. Because they're a dense resource and there's a lot of physical parameters in them, and it's all contained within one chart, you can, again, be given 2 and determine like 7 different things. And that's why they're so useful. And they're one chart among many that chemical engineers use. I've listed a few here: Cox charts, enthalpy diagrams, T, XY, PXY, and a few different others. I'd say that these are among the more complicated ones. So if you can master these, the other ones will fall in relatively easier. And they facilitate a faster and richer completion of mass and energy balances, and I've hit on that a few times. And a lot of the problems that I think you're going to see are going to be based on your ability to read the chart. All of the information's there. You just need to be able to decipher it. So bear that in mind when you're given problems based on psychrometrics. And they don't disappear from the curriculum. In separations, or CBE 25-23, you cover drying, evaporation, and a few different other separation processes involving airflow. Whenever there's airflow, there's a chance that it's wet airflow, and then psychrometrics come in. Same thing with transport 2, or CBE 35-21. Evaporation and drying those two separation processes that I've mentioned are instances of mass transfer where water is transferred from one airflow to another, and then psychrometrics come in again. And then in your career, many manufacturing ops use some sort of drying within their chemical process. That example we just went through was actually modified and changed up just a bit, but it was based on an example that I actually had in an internship when I worked for Smuckers in 2019. And we were working on a project. It was a pet food plant. We did have dryers, but they were like big industrial dryers. They were like the size of my house. They were huge. We had a number of them. And the project that we were working on in aggregate was trying to make the plant more energy efficient. And the dryers they could have been more efficient, is what I'll say. So we modulated the airflow, the volumetric airflow rate and the temperatures within the dryers. And we were able to determine some of the parameters that are on those psychrometric charts, either directly or from one or two derivations. And I was able to use that knowledge from 2200 to not only converse with the engineers and the head engineer, but like add to the conversation and learn about how we might improve the dryers and the energy efficiency. And I found that really, really cool. So it does show up in these might show up in your career. And a lot of the other things that you're going to learn in this course are probably going to show up in your career. I want to conclude with some final thoughts here. And the first one is that the psychrometric charts, they really might look intimidating, but they're easy to interpret after practice, and they're a great tool. So if you're intimidated by them, the thing that I would suggest is just to practice. And if you do, I think you'll find that they'll get easier. A lot of the in-class problems rely heavily on your ability to read the chart axes and the different lines and find the parameters not given. It's all there. You just got to decipher it. And I do want to end with this. Remember, given any two parameters on those charts, you can find all of the others with the exception of sat temperature and sat enthalpy. With that, that is our introduction to psychrometric charts. Thank you guys for listening, and I hope that you have a great day. Thank you.